All right, so what we're going to look at today with this lesson is we're going to continue working with exponents, but now instead of just working on exponents that are integers, positive numbers, negative numbers, we're going to be looking at exponents that involve fractions. These are called rational exponents, and we're going to be working by simplifying different rational exponents and simplify expressions that way. So the first thing we want to look at is, this is an important point. When we're looking at these rational exponents, okay, rational numbers are fractions and decimals, things like that. Okay, so when we're dealing with rational exponents, we're dealing with exponents that are fractions or decimals. And what we're going to do first is we're going to extend or prove how these rational exponents are going to behave in the same way by using properties that we already know about integers. Okay, so we're going to be using the same properties that we found in previous lessons on adding, subtracting, multiplying, and dividing with exponents. All right, so we'll evaluate and rewrite expressions involving these fractional exponents. All right, so let's take a look at some of the vocabulary that we have. So for this one, we need to understand what a rational exponent means. Again, rational means we're dealing with fractions today. Okay, it could also be decimals, but for our purposes today, it's just going to be fractions. So what that means is we're going to have numbers or variables. So let's say we had a number, but now instead of our exponent being a whole number like 2 or negative 2, right? Today we're going to be looking at exponents that have fractions. So what happens when we have an exponent that's a fraction, like 1/2 or 2/3 or 3/5? Any of these possibilities. What do we do with fractions as exponents? That's what we're going to be looking at. We're also going to be introducing the idea of a cube root. So we already know what a square root is. Right? The square root of a number is the factor that is multiplied by itself to get that number. So the square root of 36 is 6 because 36 is equal to 6 squared. Right? So one way to think of square roots is square roots are the inverse. Right? Square roots are the inverse of squaring a number or an exponent of 2. Right? So if we have an exponent of 2, we reverse that by doing the square root. Well, the same idea applies to a cube root. It's the inverse of an exponent with a power of 3. Right? So if we have a number, we'll say x, and we raise it to the 3rd power, okay? Taking the cube root would undo that. So we use the same symbol, we use the same radical symbol, but we're going to actually give this radical a power, and we're going to note that over here right by the check mark. Right? So that little 3 there, that tells me that it's a cube root. We're looking for the 3rd root of x to the 3rd. And in the same way that square root undoes squaring a number, the cube root undoes cubing a number. So the cubed root of x to the 3rd would just be x. Right? The cube root of 2 to the 3rd would be 2, and so on. The cube root of 3 to the 3rd would be 3. And you can keep going. The cubed root is always the opposite, or it's the inverse of cubing a number. All right, so our first rule here is that when we have an exponent to the 1/2 power, so this is very specific, we raise a number to a power of 1/2. That's the same thing as taking the square root of that number. Right? And what we want to do is we want to do a couple of proofs to show that that works. Why is taking a number to the power of 1/2 the same as doing the square root of that number? Well, let's start with, we'll use the example that they give us here, 16 to the power of 1/2. Okay. Well, we're going to use kind of some of our rules that we used before. So one of the rules that we came up with before was that when we had a power or a number raised to a power, x to the a, let's say, and then we raise it to another power, what did we do with those exponents? Well, we multiplied them together. So if we raise one number to another power, we multiply those exponents. Okay. Well, 16, I can rewrite 16 using exponents, right? 16 has different factors. It's got 1 and 16 as factors, 2 and 8. It's also got 4 and 4, right? So 16 to the 1/2 power is the same thing as saying 4 times 4 to the 1/2 power. Right? I can rewrite 16 as 4 times 4. And 4 times 4 I can rewrite using exponents because I'm multiplying the same thing times itself, so that's like 4 squared to the 1/2 power. Right? So I rewrote 16 as 4 squared. Now I can use my rule that says if I've got a power of 2 raised to the 1/2 power, I can multiply those two powers together. So I can do 2 times 1/2. Okay. Well, what is 2 times 1/2? 2 times 1/2 is 2 over 2. And 2 over 2 is 1. All right, so hopefully you're able to follow through with that. 2 times 1/2 is 2 over 2. And 2 over 2 is the same thing as 1 whole. And 4 to the first power is 4. So now, is that the same? Hopefully that shows that that's the same as taking the square root of a number, right? If we had 16 to the 1/2, we're saying that that's the same as the square root of 16. Well, the square root of 16 is in fact 4 because 4 times 4 is 16, so it's one of those equal factors. So 16 to the 1/2 is the same thing. It got us the same result as doing the square root of 16. Right. Let's try another one. Let's do, we'll do 36 to the 1/2 power. We want to prove that that's the same thing as doing the square root of 36. So 36 to the 1/2 power. 36 has two equal factors, 6 times 6. And if I write out 6 times 6, I can simplify that as 6 squared. Then again, I'm going to use my rule that says if I am raising a power, like 2, to another power, I can multiply those exponents together. So I can do 6, and then I can multiply 2 times 1/2. And just like before, 2 times 1/2 is 2 over 2, which is the same as 1 whole. And 6 to the first power is just 6. And I also know that the square root of 36 is also 6. So I got the same thing. So by showing that raising a number to the 1/2 power is the same as taking the square root, which we did in two examples here. 16 to the 1/2 got us the same thing, 4, as taking the square root of 16. It was 4 in both cases. 36 to the 1/2 power gave us 6, which was the same thing as the square root of 36. It's also 6. So by using these two examples, we've been able to show that anything to the 1/2 power is the same thing as taking the square root of that number. And so let's take a look at a couple of examples here. So 81 to the 1/2 power. And again, we're going to use the rule that we just came up with, which was anything to the power of 1/2 is the same thing as taking the square root of that number. So if I'm doing 81 to the 1/2 power, that's the same thing as saying, what is the square root of 81? And I know 81 has two factors that are the same, right? 81 is the same thing as saying 9 times 9 or 9 squared. And then I know that taking the square root of a square undoes itself, right? The square root of 9 squared would just be 9. So 81 to the 1/2 power is 9. Here we've got the square root of 38. We want to change this. Right now it's in what's called radical form. It's written using the radical symbol, like this. We want to change it so that it's written using an exponent. So the square root of 38, we're going to use the same rule that we've been going with here. B to the 1/2 power is the same as the square root of b, but we're going to use it in reverse. So if I have the square root of a number, I can go backwards. I can change that to 1/2. So if I have the square root of 38, I can say that's the same thing as doing 38 to the 1/2 power. And so it's just rewriting it in same expression, just written in two different ways. The square root of 38 is the same thing as saying 38 to the 1/2 power. All right, this one is written in exponential form, and we want to change it to radical form. So we want to change it to radical form. So we want to write this using roots. So same thing as before, b to the 1/2 is equal to the square root of b. That's our rule. But looking at this, I've got 12m to the 1/2 power. And you need to be careful because what is the power of 12 here? 12 is to the first power. M is to the 1/2 power. So I'm really doing 12 times m to the 1/2 power. So 12 I leave alone. M, I can rewrite that as the square root of m, because now it's in radical form. Went from exponential to radical, and anything to the power of 1/2 is taking the square root. And when you'll see it written like this, you'll see it kind of combined together. Won't be 12 times root m, it'll just be 12, and then the 12 goes right up against the radical symbol. Just like when we multiply, like if it was 12 parentheses m, it's right up against it, so that means multiplication. It's the same idea here. 12 being right up against the radical shows that this is 12 times the square root of m. Now again, for this you need to be careful because 12m to the 1/2, you would be tempted to say, okay, well 1/2 power means I'm going to take the square root of 12m. And that's not the case here. Because 12, like I said up here, 12 has a power of 1. M is the only thing raised to the 1/2 power. If you had 12, the square root of 12m, what you're saying is that the entire thing, 12m, is being raised to the 1/2 power. And that's not what we had here, right? Because when we had, remember our rule that said if we had a product raised to a power, we could raise each part, each factor to that power. So if we had 12m, the whole thing raised to the 1/2, which is what we're showing here, right? That would be saying then it's 12 to the 1/2 and m to the 1/2 power, which is not what we started with. Notice we've changed what the power of 12 was. So this whole thing down here, you might be tempted because you see 12m to the 1/2 to write the square root of 12m, but that one is incorrect. This up here, this is the correct way of doing it because m is the only thing being raised to the 1/2 power. So m is the only thing that you can write as a radical. And for an extension of kind of what I just talked about, what we have here is the square root of 32w. All right. So again, we're going to use this rule that says anything to the power of 1/2 is a square root, or if we have the square root of a number, we can write it using an exponent of 1/2. So in this case, what's being raised to the 1/2 power? It's the entire thing. We're doing the square root of 32w. So we're technically taking the entire thing and raising it to the 1/2 power. Okay. So 32w to the 1/2 power, the entire thing is being raised up because the entire thing is under the radical. All right, so it's important to use these parentheses to show that the entire thing is being raised to the 1/2 power. Now I'm going to show you, continue on with this just so we can, when we go to simplify radical expressions in a different lesson, you'll kind of have a good background information on this. So let's extend this out using some of our rules. We already know that if we have a product raised to a power, right? Each part or each factor of that product gets that power, right? So 32w to the 1/2 means that I could say this is 32 to the 1/2 and w to the 1/2. They're both to the 1/2 power. Well, then let's keep going with this. Let's extend this and say, all right, if I have anything to the 1/2 power, that's a square root. So I'm doing the square root of 32 and multiplied by the square root of w, right? Because each of them were to the 1/2 power, so I could take the square root of each of them and multiply them together. So one thing to keep in mind is that when you have a product under a radical symbol, okay, we can split up that product and take the roots of each part without changing it, which is what we just did here, right? If I say this whole thing is taking the square root or being raised to the 1/2 power, right? 32w is being raised to the 1/2 power. That means each part is also being raised to the 1/2 power. 32 to the 1/2, w to the 1/2. And that's the same as saying the square root of 32 and the square root of w. So by starting with this original part here, the square root of 32w, what we just showed here was that it's the same thing as saying the square root of 32 times the square root of w. And that's going to come in handy later on when we need to simplify radical expressions, being able to split up any products that are underneath a radical symbol and taking the roots of each part of those. But for now, all we need to worry about is that the square root of 32w, to write it as an exponent, would be 32w raised to the 1/2 power. All right, so now it's your turn to go through a couple of examples and see if we can get the correct answers here. So write 16 to the 1/2 in radical form. So basically simplify, what is 16 to the 1/2 power? And you should have gotten 4, because again, we're raising something to the 1/2 power, so we're taking the square root of it. So if we've got 16 to the 1/2, that's the square root of 16. And I know the square root of 16 is 4, right? Because 4 squared is 16, which means the square root of 4 squared is, in fact, 4. All right, let's move on to the next example here. So this says that for any real numbers, a and b, and any positive integer n, if we raise a to a power to get our second number b, a is the nth root of that number. And all that's saying is that if I have x, and let's say I raise it to the third power, okay, and I get a number y, right? X to the third power is equal to y. Well, if I take that number that I got, y, and I want to get back to x, I need to take a root of that number, and the root needs to be the same power as the exponent that I started with. Right? So if I started with x and I raised it to the third power, to get back to x, I need to take the third root of the number that I got. Okay? So let me pull a couple more examples here. What if it was x to the fourth power gave me y? Well, then to get back to x, I would need to take the fourth root of y. And that's where you just pay attention here where I'm putting the little number next to the root, the radical sign. That tells me what root I'm looking for. And just like square root is the opposite of squaring a number, the third root is the opposite of raising something to the third power. Right? The fourth root is the inverse of raising something to the fourth power. If it was to the fifth power, then I would take the fifth root of that number to get back to x. Okay, so basically any number being raised to a power, right? If we take the root with that same power, it inverses itself. It's the opposite. Okay, it undoes it. Just like addition and subtraction undo each other, multiplication and division, roots with certain powers undo exponents of those same powers. Right? So what we're looking for here is the fourth root of 256. So what I'm interested in is what number, x, raised to the fourth power makes 256. Okay? So let's start at the beginning. We're trying to figure out what number, if I multiply it by itself 4 times, gets me 256. Well, if I say 2 to the fourth power, that's 2 times 2 times 2 times 2. That's 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So it's not 2 to the fourth. 3 to the fourth power, 3 times 3 times 3 times 3. 3 times 3 is 9, and 9 times 9 would be 81. So it's still pretty far away, but notice this is a pretty big jump from 2 to the fourth power being 16 to 3 to the fourth power being 81. We only went up one number, but we made a huge jump in our final answer, in our final product. So that just shows you, like when you're working with exponents, the increases, it doesn't take much to make big jumps in your final product. So if we do 4 to the fourth power, 4 times 4 times 4 times 4, well, 4 times 4 is 16. So if I've got 16 times 16, that's going to give me 256. So it's actually 256 is equal to 4 to the fourth power. So if I'm taking the fourth root of 256, I can rewrite 256 as 4 to the fourth power. And I know that whatever root of the radical, if the exponent is the same as the radical, they cancel each other out, and we're left with just that base number. So if I'm taking the fourth root of 4 to the fourth, that's going to be just 4. These two 4's here cancel each other out. So 4 to the fourth power, and then I take the fourth root of that, I'm left with just 4. All right, so for this one, the sixth root of 15,625. So I'm looking for what number to the sixth power will make 15,625. Right? And I'll just go ahead and tell you that 16,625 is the number 5 multiplied 6 times. Okay? So it's 5 to the sixth power is 15,625. Right? So I can rewrite this as the sixth root of 5 to the sixth power. Okay? And again, what we said was that if we're taking the nth root of a number to that same power, they cancel each other out and we're left with just the base. So if I'm taking the sixth root of 5 to the sixth, the two powers cancel each other out and we're left with just 5. All right, so go ahead and try this one on your own. What is the fourth root of 2,401? And you should have gotten a correct answer of 7. So when you're doing this, you're looking for the what number will give you, what number to the fourth power will give you 2,401. So if we're taking the fourth root of 2,401, I'm interested in what number to the fourth power is equal to 2,401. And so if I look at my answer choices here, some of these I can probably right away eliminate, because I know if I take 343 and I raise it to the fourth power, that's going to be 343 times itself 4 times, and that number is going to get pretty huge. Right? 343 times 343 times 343 and so on. That's going to be a lot bigger than 2,401. Same thing, 81 to the fourth power. If I do 81 times itself 4 times, that's going to give me a really, really large number, a lot bigger than 2,401. So that leaves me with really realistically 2 options here. So these two don't really make sense to raise to the fourth power. 49 and 7. Remember what we said when we were looking at the examples, right? It didn't take much for the number to go for the final product to get big once you're doing exponents. So if you're doing 7 to the 4th power, 7 times 7 times 7 times 7, I know 7 times 7 in both of these cases is 49. So if I multiply 49 times 49, what do I get? 49 times 49, so that's 81. Carry the 8. 36 plus 8 is 44. 0. 4 times 9 is 36, so carry that up there. 16 plus 3 is 19. Add these up. 1, 10, 13, 14, 2,401. So 7 to the 4th power gets me 2,401. So I can say that the 4th root of 2,401 is the same thing as the 4th root of 7 to the 4th power. And again, if we're taking the nth root of a number to that same power, it cancels out. We're left with just the number. So the 4th root of 7 to the 4th is just 7. All right, for these next rules, we're going to kind of combine them and understand what they're saying. So for any positive real number b and any integer bigger than 1, so an integer more than 1, that would be 2, 3, 4, 5, 6, 7, and so on. Okay, those counting numbers above 1. They're saying that a number raised to the 1 over n power is equal to the nth root of that number. Okay. Let's take what we already know. We know that b to the 1/2 is the square root of b. Right? So in this case, n is 2. Right? The fraction 1 over 2, and then the power in the radical is 2. Well, what this rule is saying is that if b was to the 1/3 power, that's the 3rd root of b. If b was to the 1/4 power, that's the 4th root of b. All right, and we can kind of prove this using the example that's here. So 8 to the 1/3, we want to prove that that is the same thing as saying the 3rd root of 8. So let's again use our rules for exponents. So 8 to the 1/3 power. 8, I can rewrite that as 2 times 2 times 2. Okay? 2 times 2 is 4, 4 times 2 is 8. So 8 is the same thing as 2 to the 3rd power, and then raised to the 1/3. And again, if we think back to our exponent rules, we had a power raised to a power, we multiplied them together. Right? So 2 to the 3rd raised to the 1/3 power is 2 to the 3rd times 1/3. And if I multiply 3 times a third, that's 3/3. And 3/3 is 1 whole. 2 to the 1st is just 2. So 8 to the 1/3 simplified using our exponent rules down to 2. Well, that's the same thing. If I took here, the 3rd root of 2 to the 3rd is also 2, because those 3's would cancel each other out. The 3rd root of 2 to the 3rd is 2. So 8 to the 1/3 was the same thing as taking the 3rd root of 8. Right? And we could do this with a lot of different examples. We could say 16 to the 1/4 is the same as the 4th root of 16. 16 to the 1/4 is 2 to the 4th to the 1/4, which is the same as 4th root of 2 to the 4th power. So either way, we get 2. Okay? So the rule is saying that anything raised, if we have a fraction, 1 over a number, okay, that's the same thing as saying the nth root of that fraction or that number. Right? And this kind of goes beyond this also. So what if it's not 1 over a number, but it's the fraction is one number over another number? Right? The rule for that is going to be this. So let's take the example that's here, 8 to the 2/3. Right? We want to prove that that's going to be the same thing as the nth root of the number raised to a power. So 8 to the 2/3. Well, let's think about what this 2/3 represents. A couple of our rules for exponents. So again, if we think about x raised to a power, raised to another power, and then multiplying those, can I rewrite 2/3 as a multiplication problem? Well, 2/3, let's go over here, 2/3 is the same thing as saying 2 times a third, right? Or 1/3 times 2. Same thing, 1/3 times 2/1. So let's rewrite this 8 to the 2/3 as 8 to the 1/3 times 2/1. Right, so all we did was we took 2/3 and we split it up into a multiplication problem, 1/3 times 2. All right, so that we're kind of at this point here, right? We're multiplying two numbers in the exponents. So I could rewrite this going back this way. I can say that 8 to the 1/3 times 2 is the same thing as saying 8 to the 1/3 raised to the second power. Okay, so we're using our exponent rules, we're just working backwards. And then what did we learn in the last problem, or in the last rule? We said that any number to the 1 over n fractional power is the nth root of that number. So if I'm doing 8 to the 1/3, that's the same thing as doing the third root of 8, and then raising that to the second power. So notice what we did. We started with a number, a fraction, 2/3, and it became the third root of 8 squared. Let's take another one. If we do 25 to the 5/2 power, 5/2 power. Let's do the same thing. Let's split 5/2. So we're doing 25. Let's do 1/2. 1/2 times what makes 5/2? 1/2 times 5. So I took 5/2 and I split it up into 1/2 times 5. And I already know that b to the 1/2 power is the square root of b. So if I'm multiplying these, that's the same as saying 25 to the 1/2 power raised to the 5th power. Right? And I know anything to the 1/2 power is saying the square root of that number and then raising it again. So all this rule proves is that we can take a number raised to a fractional exponent, okay, and write it as a radical. The denominator of the fraction right, the denominator of the fraction is the power of the radical. All right, hang on here. The numerator is the exponent that the entire thing is being raised to afterwards. Okay, so any number that I start with, my base goes under the radical sign. The power of the radical, or the degree of the radical, is the denominator from the fraction. The numerator becomes the power of the entire thing. And you'll see what that looks like in a couple of examples here. So let's start with this first one. It says evaluate these type of expressions. So if we've got a number to the 1 over n power, we're looking at the nth root, not 3, the nth root of that base. So 1,331 to the 1/3 power means I'm looking for the third root of 1,331. So that means I want to know what number to the third power is equal to 1,331, and that's going to be 11. 11 to the third is 1,331. So I can rewrite that as the third root of 11 to the third power. And again, using the other rule that I know, it's that when I have the nth root of a number to that power, they cancel each other out, and we're left with just the number. So the third root 11 to the third is 11. So 1,331 to the 1/3 power is 11. All right, same idea, 2,401 to the 1/4 power. According to our rule, we've got 1 over n, so that's the nth root of that number. So we're looking for the fourth root of 2,401. So then again, think back, what number to the fourth power makes 2,401? If you think back to just a couple of examples, we saw that it was 7 to the fourth power is equal to 2,401. So here, we're looking for the fourth root of 7 to the fourth power. And again, the nth root of a number raised to that same degree or that same power cancels out. So the fourth root of 7 to the fourth is 7. So 2,401 to the 1/4 power is 7. All right, try this one on your own. Simplify 4,096 to the 1/4 power. And you should have gotten an answer of 8, because what you're looking for is the fourth root of 4,096. So what number to the fourth power makes 4,096? All right, that would actually be 8 to the fourth power. So we're looking for the fourth root of 8 to the fourth power. And again, our rule says that the nth root of a number to that same power is just the number. So the fourth root of 8 to the fourth is 8. All right. So here we're going to use the rule that we came up with. It says a number raised to a fraction. And we can rewrite it as the nth root of the number raised to the numerator. So whatever's in the denominator becomes the degree of my radical, and then the numerator is the exponent or the power of the entire expression. So 32 to the 2/5 power, I can rewrite this as the fifth root of 32 raised to the second power. So that 5 goes there, the 2 goes there. Right? So now I want the fifth root of 32. So what number to the fifth power would get me 32? Well, that would be 2. 2 to the fifth power is 32, right? Because 2 times 2 times 2 times 2, that's 2 times 2 is 4. 4 times 4 is 16, and 16 times 2 is 32. So we've got the fifth root of 32, which is the same as 2 to the fifth power. And our other rule, again, if we're taking the nth root of a number to that power, it's just the number. So the fifth root of 2 to the fifth is just 2. Right? The fifth root cancels out that power. And we're left with 2 to the second power, and 2 to the second power is 2 times 2, or 4. So 32 to the 2/5 power simplifies all the way down to 4. All right, let's try 81 to the 5/2. So if we start with our rule that says we have a fractional exponent, we're going to rewrite it as a radical. N is the degree raised to the numerator. So 81 to the 5/2 power, 5/2 power, means I'm taking the square root of 81 raised to the fifth power. So I don't need to write this 2 here. I did just so you could see the relationship from the denominator to the radical. and then the 5 would travel over here. All right, but when you write it, you don't need to write it as the square root. But for our purposes, we can. So what number squared would be 81? Well, 9 squared is 81 because 9 times 9 is 81. All right, so if I'm taking the square root of 9 squared, right, and again, if I'm taking the nth root of a number to that same power, it cancels out. So the square root of 9 squared is just 9, and then 9 to the 5th power would give me 59,049. Because 9 to the 5th is 9 times 9 times 9 times 9 times 9. So a really big number, 59,049. So 81 to the 5/2 power reduces to 59,049. All right, now it's your turn. Simplify 36 to the 3/2. So you should have gotten A, 216. So again, using what we know, which is that when we have a number with a fractional exponent, right, we write it as a radical. The denominator is the degree of the radical, and then the numerator is the power of the entire thing. So 36 to the 3/2. So that means I'm doing the square root of 36 and then raising that to the 3rd power. In order to simplify that, I know that what number squared makes 36? Well, that's 6 squared. So I can rewrite this as the square root of 6 squared, and then follow that rule again that says the nth root of a number to that power cancels it out, right? So the square root of 6 squared is just 6, and 6 to the 3rd would be 6 times 6 times 6. So that's 36 times 6, which is 216. All right, so that's the end of the lesson on rational exponents. Hopefully some of those rules you're able to follow in order to simplify these expressions. There's a really important rules here that you should be able to follow, and hopefully you're able to see the connection between fractional exponents and what we do with square roots and different radicals. All right, we're going to come back to these rules as we learn how to simplify different radical expressions. But for now, hopefully you're able to understand how to use the rules that we already know about exponents and apply them to fractions and see the relationship then between those fractional exponents and how we can take radical expressions and square roots, cube roots, and different degrees of radicals.